So it's been a minute since some of you talked about SN1, SN2, E1, and E2. It's been a bit longer since others of you have talked about SN1, SN2, E1, and E2. We're basically rolling into this semester expecting that you remember what all of those reactions are as it pertains to alkyl halides, and all the associated details like rate determining steps and rate laws and all that kind of thing, stereochemistry, what kind of intermediate it goes through, that kind of stuff. We're assuming that you remember all of that, SN1, SN2, E1, E2, as it applies to alkyl halides, because we're moving on to SN1, SN2, E1, E2 of other substrates next. So, I'm going to take a quick minute to recap what SN1, SN2, E1, and E2 are with alkyl halides as a substrate. SN2, you need a not crowded substrate. So we could think of something like that alkyl halide. That's a primary alkyl halide. And we can add some sort of good nucleophile. Hopefully you remember the details of who's good and who's not good nucleophiles. This is a good nucleophile. We're going to attack the carbon that has the bromine, kick the bromine out. SN2. And that's my product. Bromide was my leaving group. And I made that sulfide. That's sulfur with two carbon groups connected. It's also sometimes called a thioether. So I made that thing when I did that SN2. The rate law for an SN2, remember? K equals substrate times the nucleophile. The concentration of both of those affects the rate. Increase the concentration of this guy, you get a faster rate. Increase the concentration of that guy, you get a faster rate. SN2. That's the quickest recap of SN2 that we're going to do. Oh, one more thing. You get inversion of configuration, right? This was not an asymmetric carbon, so it doesn't really matter here. But if this were an asymmetric carbon, you get inversion of configuration over there. SN2. Okay. What about SN1? SN1 goes through a familiar intermediate. It's probably become our favorite intermediate. We'll see more of those this semester. It goes through a carbocation. So you need a crowded substrate, like that tertiary alkyl halide, in order to do SN1. That tertiary alkyl halide, let's put in some water. Why not? Big leaves, and leaves behind a carbocation. Water can attack that carbocation, like so. And then water cleans up the mess that was left behind to give you this alcohol product. You haven't forgotten your function groups, right? Right? Yeah, hope not. In an SN1, the rate law is rate equals K times substrate and substrate only. This is the only thing involved in the rate law because I made a carbocation in this first step, and formation of the carbocation is the rate determining step for all reactions involving a carbocation. So the rate determining step here is the first one because it makes the carbocation. Yep. SN1, because it goes through a carbocation, that's sp2 trigonal planar. So things that are sp2 trigonal planar, you're going to get a racemic stereocenter. This is not an asymmetric carbon, so we don't have to show asymmetric stuff here, dashes and wedges here. But because it came through a carbocation, this would be racemic if it had created an asymmetric carbon. That's SN1. What's common about SN1 and one of the eliminations? SN1 and E1 both go through a carbocation. So we'll do a quick little E1. I'm going to do the same tertiary alkyl halide substrate. I'm going to still add water because what we talked about with SN1 and E1 is that SN1 and E1 always come together. You can't very easily get one without the other in alkyl halide substrates, with alkyl halide substrates. So yeah, what did I do differently this time? I took not an alpha, but a beta hydrogen. Take a hydrogen from the beta. All three of those betas are equal betas, so I would make this product regardless of which beta hydrogen I take. But if I take from the beta with the fewest, that would be the Zaitsev product. Take from other betas, that's the anti-Zaitsev product, beta with the most hydrogens. Yeah, those are familiar words, right? Zaitsev, anti-Zaitsev. Things you gotta be familiar with all over again this semester. I know some of you are old, some of you are new. Just a quick recap. E1, this would be the rate determining step. Formation of the carbocation is the rate determining step. The rate law would be only dependent on the substrate. Yeah. And the stereochemistry, this is always going to create sp2 carbons. And sp2 carbons don't have stereochemistry like dashes and wedges, asymmetric stuff. You have to worry about cis and trans, E and Z. This specific example does not have any E and Z qualities, so we don't have to worry about it. But because this reaction goes through a carbocation in general, it could create E and Z products as your final alkene product. But this one's just going to create this, which is not E or Z. It's not applicable. So like I said, we will get SN1 and E1 mixtures, but we have also said that one thing you can do to kind of promote elimination over substitution is crank up the temperature. If you heat this reaction, the entropy favors elimination over substitution. So thermodynamically, heating this reaction causes elimination to be favored. So if we add this same substrate with water and heat, we would expect E1 to be the major pathway followed. If we added this tertiary alkyl halide with water, we would expect SN1 to be the major pathway. Again, they always come together, but if you add some heat, you can favor one over the other. All right, and finally, what about E2? E2 can work with crowded substrates, so that's something that's a little bit different, E2 versus SN2. You need a strong base. Naomi, OMI minus, is a strong base. In E2, you're going to pluck a beta hydrogen, simultaneously dumping in electrons to make a new carbon-carbon pi bond and kick out bromine. The fancy word for all that happening at once is concerted. E2 is a concerted mechanism. One step, all in one time. Pluck an alpha. Nope. Pluck a beta hydrogen. And dump in electrons, kick out your leaving group. Yep. E2. E2, because it's concerted, you have to worry about the stereochemistry. You have to worry about the H and the leaving group being anti-periplanar. If you hadn't been with us recently, you remember what anti-periplanar means, right? It's your job to go review that if you don't. We could talk about the kinetics of this reaction. The rate law would be dependent on the substrate and the base, because it's E2, elimination bimolecular. Yeah. That's a quick little recap of all the SN1, SN2, E1, and E2 stuff, all stuffed into one little tiny review package with alkyl halides. Did we mention every single thing you need to remember? Unfortunately not, but we hit the highlights. Maybe that's good enough to get us started. Why does all that matter? Because there are a lot of other groups that can undergo substitution and elimination as well. Anything that has an sp3 carbon connected to an electron withdrawing group could undergo substitution and elimination. The weaker the base, the better the leaving group. So in our alkyl halides, like this thing, in our alkyl halides, when a nucleophile came and attacked, or when an alpha hydrogen dang it, when a beta hydrogen was plucked, we let go of an X minus. That's a halogen with a minus. This substrate could also undergo substitution or elimination. You would let go of an O, S, O, O, R. That O that let go is a minus. This substrate could undergo, let's say, SN2. If a nucleophile attacks here, we could let go of a sulfur with an RR, like that. If a nucleophile attacks here, we can kick out that and get an OH minus. If a nucleophile, I'm drawing these as if it's SN2 every time, but we're just talking about potential leaving groups is what this is about. If a nucleophile attacks here, we get that. So this yellow highlighted bit up here says weak bases make good leaving groups. If we look at all these potential leaving groups down here, this is the weakest base, and this is the strongest base. So these are actually ranked in order from weakest base to strongest base. Strong bases are bad leaving groups, as in this thing over here, not a good leaving group whatsoever. Neither is this nor that, not a good leaving group. These last three, the leaving group is too strong of a base to be a good leaving group. But the first three, those are pretty good leaving groups. We've seen alkyl halides for a whole long time with a bunch of examples before. Alkyl halides are great leaving groups. So remember, that's alkyl halide. We have not talked about this functional group yet, but that functional group we're learning now is a sulfonate ester. This guy, sulfur with a positive, is a sulfonium ion, sulfonium salt. This is alcohol. We've been talking about alcohols for a long time. Ethers and an amine. We said these three have terrible, horrible, no good, very bad leaving groups. But there's all our leaving groups in legible form. But an alcohol, this is a bad leaving group. It's a terrible leaving group. But that alcohol could be protonated first to become like this, and then water could leave from that protonated alcohol. So water could also be my leaving group from an alcohol. Same deal with an ether. This top one is a terrible leaving group. That's a strong base, terrible leaving group. But that O could be protonated first, and then it could leave as a neutral alcohol. So alcohols and ethers have naturally bad leaving groups, but if you react alcohols and ethers in acid, the acid can turn alcohols and ethers into reasonable leaving groups because these bases are weak enough bases to be good leaving groups. An amine is going to be an N- regardless. If you protonate this amine, that's not going to be a good leaving group either. We'll talk a little bit more about amines, but some other stuff goes awry with this amine. If you try to protonate it and make a decent leaving group, it's not going to happen. So this amines are not good at substitution. Amines are not good at elimination. Amines are going to be something we talk very little about within this chapter. That was a very brief, quick recap of SN1, SN2, E1, and E2 as it applies to alkyl halides. And this is a preview of what's to come next. We will start with reactions of alcohols, remind you of old reactions to make alcohols, and tell you about new things to do with alcohols. Coming soon.